growth and decay. First one, decay. Kind of like fossils decay, right? What else decays? Teeth decay. I don't know. What else? Did you say Blake?
No.
Bodies, yeah. Our exponential decay function looks like this, where we have a coefficient out front. The important part is this b to the x power. Okay? When it's a decay function, your b is a fraction decimal between 0 and 1. Okay? Can't equal 1, can't equal 0, but in between there. Okay? So, for example, if I had like 0.98 to the x power, that's a decay function. Okay? It kind of makes sense because it gets smaller if it's less than 1. Okay, that's how I would think about it. Oh yeah, not morbid stuff. Cars, houses can lose value. Money can lose value. That's decay functions that aren't so morbid. Alright. So, graphing exponential functions. If I have the function y equals 4 to the x power, we're going to do this using a table, okay? Cross out your -3 because that gets too small. So if I have y equals 4 to the x power, and my x is -2, I have 4 to the -2 power. Okay, just plugging in -2 to x. Remind me what negative exponents do. Decimal. 1 over. So this is like 1 over 4 squared, right? What's 4 squared? So my y value is 1 over 16. Okay? So if my x is -2, my y is 1/16, so my point would be -2, 1/16. Okay, that middle column's there just kind of to help you visualize what's happening, where to stick it in. My x is a -1. Same thing, I have 4 to my x power. X is -1. What does that make my y value? 1/4. Good. Okay, if my x is 0, I have 4 to the 0 power. I don't think we've talked about this. What is anything to the 0 power? 0 itself? 1. Anything to the 0 power is 1. Okay, then we get to normal things like 4 to the first power. What's 4 to the first power? And 4 to the second power? 16. Okay, good on plugging in? Okay, now what we're going to do is plot these points. Like I said, this is our x, and this is our y, so kind of ignoring that middle column. So we'll graph -2, 1/16. No, it doesn't have to be perfect. Mine's definitely not going to be perfect. 0, 1, 1, 4, and 2 goes like way up there. It turns out to be a smooth curve where it kind of looks like it touches the x-axis. But do we ever hit 0, do you think? No, you just get like microscopically close? Microscopically? Whatever, you get super close. Very close. Okay, but it never actually hits 0. Okay? As you can see, it goes up super fast, super quick. So we just kind of draw straight lines up. They're not exactly straight, but I feel like we kind of get the picture. Maybe. Okay, so our exponential functions will always have this curve to them where they get really close to some value both x and y. Okay. Questions so far? Alright. This just kind of tells you basic functions again, that a to the bx power, our a is always greater than 0. Okay, so if it's nothing's there, a is 1. Remember, if it gets bigger than 0, that's kind of like a stretch. Okay, that same sort of thing. If my b, so b is the thing that's taken to the power. Okay, a, you'll notice, isn't taken to my x power, it's just b. The b value will tell us if it's a growth function or decay. Like we said, if it's in between 0 and 1, that's a decay function. If it's greater than 1, it's a growth function. Okay? Does that kind of make sense? Bigger than 1 growth, less than 1 decay. So let's move on to 7. It says, write d if the function's decay, g if it's growth. If I look at 3 to the 5x, 5 to the x power, is that a growth or decay? Growth, yeah. Is that because of my 3 or my 5? My 5. My 5 is the one getting taken to the x power. Okay, so that's what I'm looking at to determine if it's growth or decay. What about half times 7 to the x power? Growth. Why? Because I'm only worried about my 7, not my half. How about 35 times 1/3 to the x? Decay. And my last one, 0.25 to the x power. Decay. Because my 0.25 is between 0 and 1. Okay. Let's throw another one in there. I have 2 times 3 to the negative x power. You think it's decay?
No. Wait, no, that's decay.
What does my negative exponent do?
1 over.
1 over. So isn't this the same as I take my 1 over? So is it a growth or decay? It's a decay. So if you have a negative exponent, look at what your b is. Okay? If it's bigger than 1, you actually have decay. If it's less than 1, you have a growth. Okay? I would just get rid of the negative exponents and then make my determination that way. Okay? What other thing? Our y-intercept, so where it crosses the y-axis, is always at our value a being whatever is multiplied, whatever our coefficient is outside. The reason that is when I plug in 0 for x, anything that's 0 higher we said is 1. So 1 times our a is always going to be our intercept. Okay? Asymptote at y equals 0, that's our x-axis. So every value we have, unless it's shifted up or down, is going to be bigger than 0 as far as our y values. Okay, like I said, sometimes, you know, in like our parabolas, we could go -2 to bring the whole thing down. But our general case is that everything is greater than 0 for our range. Okay. Questions on determining growth and decay? Alright. How about this one? Is 3 times 4 to the x a power of not a power, an example of growth or decay. Growth. What would my y-intercept be? 3? Do you guys agree? Yeah. My y-intercept would be 3. If you ever forget y-intercept, where it crosses the y-axis, x equals 0, plug 0 in for x. 4 to the 0 power is 1. 1 times 3 is 3. Okay. How about the next one? It's a decay. What about my y-intercept? Why isn't it 0.7? Yeah. Remember, our functions are a, b to the x. So this 0.7x is this chunk, or b to the x. A, if there's nothing there, kind of like when we have x plus 3, that's like a 1x. Okay, so when there's nothing there, it's like 1. Okay. Questions on our intercepts? Right. We can talk about rate of growth or decay with this function, where we have an amount after a certain amount of time equals our initial amounts, what we started with, times 1 plus our rate taken to the power of however long our time is. Okay? If we have a decay, obviously our rate is negative, so that's like a 1 minus our rate. Okay, so you can kind of think of this one as decay and this one as growth. Or you could put plus some negative in there. I feel like we should know if it's a decay that we shouldn't have bigger than 1, right? The cool thing is, this formula tells us about money, and everybody loves money, right? I love money. Unless you don't have it, that sucks.
Well, I can use
It says, suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will there be in the account after 5 years? Okay, so let's break this down. My $500, is that my amount after a period of time?
No, that's not what you put in.
So my initial amount?
Yes.
Okay, so my 500 is my, can I write IA? Initial amount. It's going out front.
Is this compounded interest or non-compounded interest?
Annual. So it's not compounding continuously, but it's compounding annually.
I was just wondering, like, if you'd pay 3.5% of the 500, you just keep doing that every year, or you'd add it to the 500.
Well, if it's added on, yeah, they don't take it away. What would my rate be? 3.5? You guys agree with that?
Okay.
What if I told you I was wrong? It's 5. Our rate's 3.5%. But does that mean I plug in 3.5 for R? I gotta deal with my percent. What goes into my rate isn't percent, it's decimals. How do I figure out what this is as a decimal? How do I do it? If I told you you got a 75% on a quiz, times 100, divide by 100, okay? Or move your decimal to the left. So this is 0.035. Just like 100% is 1. Move your decimal twice to the left. So this is our rate. Only other thing I need is my t for period of time. What's t? 5 years. And I need to know how much will be in the account, so I'm looking for the amount after a certain amount of time. So let's plug into our formula. Looking for my amount after 5 years. First thing that goes outside is my initial amount. Then I have 1 plus my rate, which is 0.035 to the 5th power. Okay, what happens in here? What?
You add one.
I add them. So does it make sense that I get a number greater than 1 in here? Does it make sense that it's a growth function, not a decay function? Yeah. 'Cause when you make interest, it adds money. Okay. So in my calculator, we're going to take 1.035 to the 5th power times 500. And how much money do we have? Say what, dear? 593.84. Money gives 2 decimal spots because we got cents.
That doesn't make sense.
What?
It doesn't make dollars sense.
Okay. No. God, you guys are lame. Questions here?
I have a question.
Yeah, what's up?
So does the 5 on the left side just not matter?
Yeah, that's just our amount after 5 years. You could say Y. The number you're looking for. X. Whatever.
In the word problem, how do you have to use plus or
If it's a growth, so you invest money and you're getting, because it pays, so you're getting money, so you'd be adding. Okay? Things like loses, I don't know what other words describe decay. Decrease.
Depreciates.
Sometimes it'll say, yeah, depreciates. Sometimes it'll say decay. If you don't know what a word means, get a dictionary. No, I'm just kidding. You can ask me, I'll tell you. Alright. Says suppose you invest $500 in a savings account that pays 3.5% annually, annual interest, excuse me. I want to know when our account's going to contain $650. Well, I know after 5 years we're only at 593. So is it going to be more than 5 years or less than 5 years? More. Okay. What's my $500? My initial amount, yep. What's my rate? Good. What's this 650? It's not my initial amount. What is it? My ending amount. Yeah, the stuff that we put on the left. And I'm looking for when, so I'm looking for a time. So plug it in our calculator. This is my ending amount, so it goes out on our left. Initial, same spot. Can I put this? Is that okay instead of the add?
Okay.
It's the same as 1 plus 0.035. And then I don't know how long, so to the t power. Okay, so that's our function. How can I start getting t by itself? Divide by 500. What is 650 divided by 500?
Isn't there supposed to be like
What? how to get t by itself? The t, right? Guess what? By the end of this chapter, we're gonna know how to do that. Right now, we don't. So, favorite thing ever, guess check. We said it has to be more than 5 years. Give me a year. What do you think? 8? Let's try 8. Take 1.035 to the 8th power. We go what? Somebody say it.
No, I was just guessing.
1.316. Close to 1.3, but too much, right? So what should I try next? 7. If I put 7 in, what do I get out? 1.27. 7.5. 1.29. We're getting close. 7.7. Plug it in there. What do we get? 1.30. Thank goodness. So our t is about 7.7 years. Okay. Questions? Say that again, bud.
Could you like plug that in for T and see if we get
Well, you should. If you take, well, we know this is 1.3. 1.3 times 500 better be 650. Okay. It says the value of a house grows 2.3% per year for 14 years. Is that a growth or decay function? A growth. We need to write an exponential function. So let's put our y equals. What am I going to put for my initial amount? 125,000. Am I going to have 1 minus or 1 plus? 1 plus. Can I go straight to the decimal? Okay, what's it going to be? 1 point what? 023.
Oh, 3.
To the t power. That's my model, okay? That's for our model. And then to find the amount, what am I going to do with my 14? Plug it in for t. So if I plug that in, take 1.023 to the 14th power times 125,000. Oh man.
So you have to put T at 14 right away?
For our model, yep.
171,857.
I got decimals.
Yeah, mine's 6. You're on it.
6, 7.
6. Well, if you,
Hey, those 66 cents, you never know what it could buy you.
Again,
A ring.
Not much.
So you just plug the 14 to the T.
Put in your calculator. Stickers.
Snickers?
Stickers. Probably a fun size Snickers. Alright. Value of a $25,000 motorcycle decreases 18% each year for 3 years. Oh, do I have a growth or decay?
Okay.
Decay. What's my initial amount? Do I have a 1 minus or a 1 plus? 1 minus. 1 minus what? 0.18 to the t power. Let's simplify this. What is 1 minus 0.18? 0.82. So we have 25,000 times 0.82 to the t power. And then what did you say I'm plugging in for T, Allison? 3. Plug my 3 into T. Go ahead in your calculators. I better get a number less than 25,000.
Yep.
What'd I get?
15,708.22.
That motorcycle after 3 years, lost all its value. It's almost half. Crazy. Isn't that crazy that to get money it takes forever and to lose it takes a second?
That is legit.
You can make it back.
Life.
Put it on
My
eBay.
dad trades cars like every 2 years.
Okay, we got one more. Initial value of a car is 30,000 after 1 year. The value of the car is 20,000. Find the value of the car after 5 years. Oh boy, we got a lot to do. What does my 20,000 represent?
Price now.
Why?
Yeah, the price now on my other side of my equation. Okay, so my 20,000 equals 30,000 is our what?
Starting price.
Initial. Do I know what my rate is?
No.
No. We're just gonna call it X. What's my T? What's my time? 5? You sure?
Yeah, it's fine. One.
1
year.
After 1 year, it's 20,000. Then let's find. Well, now we gotta figure out our rate first. Okay. So how do I get X by itself? Divide by 30,000. So my rate is 0.67, right?
Yeah.
Okay. Now using, I'll put an R here. My rate of 0.67, first off, growth or decay?
Okay.
Decay, because its initial value is 30, now it's worth 20. Okay. I'm looking for the value, so do I know my left-hand side?
No.
No, not for the 5 years. Then I have my initial value still 30,000. This time, what am I putting for 1 minus 0.67?
1 minus 0.33.
So is my rate that it decays 0.67? Or is it 30%?
Decays at 30%. 33%.
Isn't this number what gets taken to the T? Yeah. So our rate is 0.67 to the T power. If you wanted to figure out what the decay rate is, you would do that. No, I lied. You would have the 1 minus, if you wanted to figure out what it decayed at.
Yeah.
What am I plugging in for T? 5. If I plug 5 in, how much is my car worth? Probably nothing.
1,050.38.
Oh my goodness. After 5 years, my $30,000 car is worth $4,000. That's why you ride bikes.
No, that's what kids do.
That's why you buy the cars that are worth $4,000.
But the bike will depreciate and you'll lose the value of the bike.
Yeah.